Now we want to print our identified primes as table with a counter. And in this case I want a table with 100 columns that shows us 100 prime numbers in every single line. So we first create a string that starts with the counter, and then we use a loop that attaches 100 prime numbers to that counter and prints the complete line. The screen output can either be saved as a text file or using copy and paste to bring it into programs like Excel. And what you get looks like this. Here are the results copied from FIJI to Excel. Important question: are those primes correct? We can check this easily online. Here you have a page where you can enter a number, and the page returns you how many primes are less than or equal to the number you enter. Or you can enter a number from our counter and the page returns the according prime. And we see those numbers are primes and our counter is correct. Java and ImageJ Java are not really known for impressive speed. So let's convert the code to C++. But first we have to take a look at a few relevant differences between ImageJ script and C. In ImageJ, you would start with an array with the according number of elements. You would assign a number or a value to the already existing elements, and you should not add elements to an already existing array using a loop. This becomes devastatingly slow. In C, you start with an empty vector. You don't use arrays for really large lists of elements. You add new elements to an already existing vector, and you try to avoid sorting of really large vectors. My first attempt in C completely failed because the two vectors A and B had to be merged and sorted. In ImageJ this is no problem, but in C it became extremely slow. Here we test the failed C+ version. The task was to calculate all primes that are smaller than 5 billionths, and that's about 235 million primes. The whole computing time was about 5 minutes. It took 2 minutes from creation of the vectors to deletion of all zeros in the merged vectors. But then it took additional 3 boring minutes just to sort the results. Without sorting, we had a prime generation rate of almost 2 million primes per second, but with sorting we were only 3 times faster than ImageJ, and that's just crap. So we need a new approach. We have to avoid sorting, and it must be possible to do all this with a single vector. We will not just translate the code from one language to another, we will transfer the basic idea. And now we have to recode the idea for C++. We fill a single vector with prime candidates. Then we delete all the multiples of the single even elements E0, E2, E4. We start from element 7i plus 10, and we use in this case 2 times AI as increment. What we did previously in 2 separate arrays is now done in a single vector. First to the elements from array A, that are here the even ones E0, E2, E4, and then to the elements of array B, E1, E3, E5. And in order to delete the multiples of the odd elements, we start from element 3i to the square plus 8 times I plus 4, and we use 2 times AI as increment. And now we delete all the remaining squares of the single elements, and starting from there the according multiples. We start from element 3i power 2 plus 10 times I plus 7. We use the root of AI as increment, and after the step only primes and zeros are left in this vector. The zeros are deleted with a single command, and the missing primes are prepend to this vector. So we insert first the 3 and then the 2. And now all the primes are already in their natural order and there is no need for sorting. Time for a speed test, and we start with ImageJ. First we calculate all the primes that are smaller than 600,000. That are roughly 49,000 primes, and we can calculate them with a rate of 366,000 primes per second. The hardware limit of my machine is reached when we try to calculate all the primes smaller than 600 million. That's about 31 million prime numbers, and we still have a rate of more than 191,000 prime numbers per second. And here we can see what the C++ version is actually capable of. Calculating all primes that are smaller than 1 million, that's about 78,000 primes, can be done at a rate of 13.2 million primes per second. If you calculate all the 144 million primes that are smaller than 3 billions, you can do this still at a rate of 4.2 million primes per second. But remember, at the beginning of this video I promised you much more, and that was no clickbait. Here it comes. Do we really need the vector actually filled with prime candidates? If necessary, we can calculate the value of any element just by its position. So what happens if we start with a large vector, if we assign a 1 to every single element, and if we start replacing the elements corresponding to the non-primes with zeros? Maybe this can be done faster. First, we fill a vector just with ones. Then we delete all the multiples of the single even elements E0, E2, E4. The step size that is necessary for deletion can be calculated from the position of the according element using the formula 6i plus 10. So there is no need to read out the according element. We just count and replace first the even elements and then the odd ones, E1, E3, E5 and so on. After all these steps we replace the remaining 1 elements in the vector with the according prime numbers at that location. We remove all the zeros at the missing primes 2 and 3 and are done. Time to compare the different C++ versions. Here we use 2 different compilers to compile our ideas. Visual Studio and Dev C++. The task is to calculate all primes that are smaller than 1 billion, and that's about 51 million prime numbers. And as you can see, our version 1.1, that's the version where we insert the primes later, runs about 66% faster if compiled with Visual Studio. So we can see that the used compiler has a massive impact on our performance. Now we take our prime lister 1.1, compile it using Visual Studio and run a last speed test. And here we go. All primes that are smaller than 1 million are computed in just 4 milliseconds. 79,000 primes computed at a rate of almost 20 million primes per second. Calculating all the 190 million primes that are smaller than 4 billions brings us to the hardware limit of my machine. But we still calculate at a rate of 5.5 million primes per second. The last value, compute all prime numbers that are smaller than 5 billions, was already above the absolute hardware limit of the used machine. The speed significantly decreased, maybe due to hard disk swapping. But it still worked, nothing crashed. Let's discuss this. Memory is the limiting factor of our prime generator. The speed of the compiled exe file depends massively on the used C compiler. ImageJ is not really slow, but of course it cannot compete with C. It has less power and inferior RAM management. Nevertheless, reaching more than 19 million primes per second with C and about 360,000 primes per second with FIJI with just a few lines of code is absolutely nothing to be ashamed of. At the limit of a system using 32 GB of RAM, PrimeLister is able to identify all prime numbers smaller than 12 billions. Whatever you are going to do with a 6 GB list of primes. And compared to others, PrimeSieve is quite fast. Let's compare our PrimeLister version 1.1 to PrimeSieve 7.3. The task is I need a list of all the primes that are smaller than 10 million. Wow, so we are 67 times faster than PrimeSieve, and we even took the slow devcc compiled one. But okay, I have to admit that's not really fair, because printing on the screen takes much longer than calculating and writing data into a file. But I wanted a list to stare at the primes for hours and hours. But of course, PrimeSieve is faster. It can compute almost 250 million primes per second, or the first 50 million primes in about 200 milliseconds. At least they claim so. On the other hand, if you calculate and screen print the same task with FIJI, it takes an overall of 5.5 seconds. So whatever. What is the next step? That's clearly the parallelization of PrimeLister using Pragma. That's a little bit tricky in nested loops. The first attempts worked. All 6 cores of my processor were used, resulting in a 5% decrease of my speed. So I'm working on it. As mentioned, you can download all the material presented and discussed here. You get the source code for ImageJ and C+, as well as the compiled EXEs for C+. Feel free to use and modify. How do you use the macros for FIJI? First get FIJI, open it, and then just drop the text file containing the macro on the interface. Adjust the language to ImageJ1 macro, change some values if even necessary, and then just click run. And that's all about prime numbers for today.